So we're going to take our probability up another notch and just talk about more complicated events. So I'm first going to start out with an example to talk about a specific type of event in comparison to another. So say a card is selected from a standard deck of cards. We want to determine the probability that the card selected is a 5 and is not a 5, okay? So again, get comfortable with that deck of cards, but in total, there are 52 cards in a deck. And there are 4 5s. You've got the 5 of hearts, diamonds, spades, and clubs, okay? So my probability of getting a 5 is 4 out of 52. And again, this does simplify. Both are divisible by 4. So if you divide top and bottom by 4, that gives you 1 out of 13. And again, another way that you could have looked at this is, again, if I run through my list of cards, you've got ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. There are 13 types of cards, and we're looking for one specifically out of 13. So your probability is 1 in 13, okay? If I ask about finding the event that the card selected is not a 5, this is a little bit more complicated. So again, I'm looking at my list, and if I want not a 5, well, then I'm going to ignore that. And you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 cards out of 13 that make you successful. The other way is if you look at that full deck, you can count up how many cards are not 5s. And the way you can think about doing that is there are 52 cards in total. 4 of them are 5s. So there are 48 cards that are not 5s. So our probability of getting not a 5 on that draw is 48 out of 52. And again, it does simplify because if you divide top and bottom by 4, this indeed is 12 out of 13, which is exactly what we got from up here. There are 12 out of 13 cards that are not 5s, okay? So when you have two events like this, you have event A, which is getting a 5, and then this, what we kind of consider to be an opposite event, not a 5. We call that the complement. The complement of an event A, which is denoted by A with a bar on top, consists of all outcomes in which event A does not occur, okay? So the nice thing about this, if you think about the word complement, these two, the complementary colors is the best way to kind of think of it. They're opposites on a color wheel. Complements are kind of opposites to each other, but they form the entire space. So if you take two complementary colors, you can make a wide array of hues between the two, but these two events will take up your entire sample space because there's two possibilities. If you draw a card from a deck, it's a 5 or it's not. It's one or the other in here. So they form the entire sample space of that deck of cards, okay? So this actually leads to something that's called the rule of complements. The sum of a probability that an event will occur and the probability that it will not occur is always going to equal 1. Okay? So the probability of event A plus the probability of event not A occurring is always going to be 1. And again, using our notation with the complements, A and A complement are just putting a bar over it. So sometimes this event can be really difficult to go through happening, especially if you have words like at least getting this. Well, in that case, the complement might be an easier event to look at here. So what you can actually do is just rearrange this. If I go ahead and subtract this probability to the other side, what I get is the probability of the complement occurring is 1 minus the probability of the event occurring. Or you can switch it around. The probability of event A happening is 1 minus the probability of its complement. So if you have an event that you need to figure out and it seems really difficult, try looking at the complement. That might be something that's easier to calculate. And then you just do 1 minus that probability to get there. So to show you with this prior example, if I wanted the probability of getting not a 5, it's really 1 minus the probability of drawing a 5. And we could figure out that the probability of getting a 5 is 1 out of 13. So if you want to subtract these two, you have to make the 1 with the same denominator. So I need it to be over 13, which means I need to do the same thing in the numerator. So that's 13 over 13 minus 1 over 13. And when you subtract fractions, the denominator does not do anything. You subtract the numerator. So 13 minus 1 is 12 over 13. And so you end up with exactly the same answer I got back up here, but I didn't need to actually calculate that probability. I could use my knowledge to get there from the first part, okay? So again, if you run into a sticky situation, try looking at the complement, especially if you see words like at least. Good indication that you're probably going to use the complement, okay? So let's try a different type of problem instead. And this is going to dive more thoroughly into OR problems. So we saw a little bit of that in the last section, but what we want to do is kind of extend the idea and see, can we see a relation between OR and AND problems? Because again, sometimes finding OR could be pretty difficult. So I'm going to start with an example first, and then we'll see, can we make a note out of that? So we're going to determine the probability of rolling either an even number or a number greater than 4 on a roll of die. So again, I've got two events here. We've got evens, and then we have numbers greater than 4. So if I think of my sample space, my successful even numbers are going to be 2, 4, or 6. And then if I look at my successful numbers greater than 4, again, greater indicates that I cannot equal because those words are not here. So the numbers that are greater than 4 are 5 and 6. So as long as I roll a 2, 4, 5, or 6, I'm going to be successful for this particular event of getting an even number or a number greater than 4. So my total number of successful rolls, or my successful rolls, are any of the numbers 2, 4, 5, or 6 if I merge these two lists together. So my probability of getting an even number or a number greater than 4 is 4 out of 6. And then that does reduce. Both are even numbers, so we can divide it by 2. So that gives me a 2/3 chance of getting an even number or a number greater than 4, okay? So really what ends up happening here is if you think of these different events, if you just went and added them together, 2, 4, 6, 5, and 6, that gives you 5 possible outcomes. So a really common mistake when you're doing OR is you just add the probability of getting an even number plus the probability of getting a number greater than 4. So treating those two events separately. However, if you look, there's overlap between the two. We have 6 that fits in both categories. So what we end up actually having to do is we have to remove that overlap. So if I want to find the probability of event A or B occurring, you can indeed add the probability of each event together. But what you need to do is subtract that overlap. So that would be the probability of event A and B occurring. Because in this case, 6 occurs for both, okay? So if I think of this with my prior example, if I want to find the probability of getting an even number or a number greater than 4, based on this, I would find my probability of getting an even number. I would find my probability of getting a number greater than 4. But then I need to subtract that overlap. So I need to remove the probability of getting an even number and a number greater than 4. Okay. So using my pieces up here, my probability of getting an even number is 3 out of 6. My probability of getting a number greater than 4 is 2 out of 6, because you get a 5 or 6. So we'd add those two together, which gives you 5 out of 6. But I need to remove the probability of getting an even number and a number greater than 4. So the only possible way that can happen is if you roll a 6. That's an even number and it's greater than 4. So we have to subtract 1 6. So if I take 5 over 6 and I subtract 1 over 6, indeed, I get that same answer of 4 over 6, or 2/3. Okay. So in this event, it's not so hard to actually sit here and look at every possible outcome. But when you do have a lot going on, sometimes breaking it down in this idea of subtracting out what's common is super helpful. So let's try another example of this. Again, we're going to work with a standard deck of cards. We're going to pick one out. We're going to determine the probability of selecting specific things. So starting out, we're going to find the probability of getting a jack or a spade. Okay. So again, if I consider these two events, we're going to look at the probability of getting a jack, and we're going to look at the probability of getting a spade. So if you think about your jacks, you have a 4 in 52 chance. There are 4 cards that are jacks out of 52. Okay. Now, if you think about the spades, well, there's 4 different suits, so you can consider it to be a 1 in 4 chance. But also you can go ahead and go back to that chart and you can count up how many spades there are. But if you think about all of your possible outcomes again, you got ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. There are 13 cards, and you can have one of each be a spade. So there are 13 out of 52 cards that are spades. However, the problem is if I just go ahead and add these two together, well, you've counted the jack of spades in both of these. So if I look at the probability of getting a jack and a spade, so fitting both criterias, there is 1 card out of 52 that has both characteristics. Okay. So my probability of getting a jack or a spade is, I take the probability of getting a jack, I add the probability of getting a spade, and then I subtract the probability of having overlap. So a card that is a jack and a spade. My probability of getting a jack is 4 out of 52. probability of getting a spade is 13 out of 52. And then my probability of getting a card that is a jack and a spade is 1 out of 52. So going through, they all have the same denominator. So I go ahead and just do that operation with the numerator. So 4 plus 13 minus 1. 4 plus 13 is 17. Minus 1 gives me 16 out of 52. And again, this looks like it is divisible. Both top and bottom can be divided by 4. So this probability would be 4 over 13 when it's fully reduced. So just to kind of show you with our deck of cards, if I go ahead and highlight all the ones that make sense, if I'm getting a jack, there are these 4 possibilities here, or a spade, there are these 13 possibilities here. But again, you can see you would double count if you just add these 2 together. So if I go and count individually, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 out of 52 cards that are jacks or spades, which is exactly what we got when we broke it down to those different probabilities. Okay. So let's try another example of this. I'm going to go ahead and bring this photo down just to have. Let's go ahead and get rid of the stuff on it. Let's find the probability of getting a club or getting a red card. So again, I can sit here and I can go ahead and count all of my clubs and I can count all of my red cards, and it does work the same. But when we have really complicated situations, that's not the best approach. Because what if we need to figure out if we draw 3 cards and you put the card back in? It's very difficult to sit there and see all of my possible outcomes in that sense. So it's going to be better to break it down by those distinct events. So my first event is getting a club. So if I want the probability of getting a club, that looks terrible. Let's see if we can make that a little better. Tiny bit. There are 13 out of 52 cards that are clubs. If I want the probability of getting a red card, again, you can sit there and add that up, but you have a 1/2 chance because it's either red or it's black. So there are 26 red cards out of 52. Okay. So again, think of this as there's 13 hearts, which are red, and 13 diamonds, which are also red. So that's the events individually. Now, if I look at the probability of getting a club and a red card for that overlap of the events, well, in this case, there are no cards that are clubs and red because every single club is a black card, so there's no overlap between the two. So when I go to find this probability of a club or a red card, following our formula, it's the probability of getting a club plus the probability of getting a red card minus the probability of getting a card that's a club and is red. So in this case, we have 13 over 52 plus 26 over 52, and then minus absolutely nothing. So that end event did nothing at all. So if I go ahead and add these 2 together, my denominator is still 52. 13 plus 26 gives me 39. And then this we can simplify. If you take top and bottom and divide it by 13, that's going to give you 3 over 4. So you have a 3 in 4 chance of getting a card that's a club or a red. And again, you can see that just from up here. You got 1 whole row, 2, 3 out of 4 rows that are clubs or red cards, okay? So when this happens, when there is no overlap in the event, we have a special terminology for it. These are really nice types of events, especially for finding probabilities. So we say 2 events are mutually exclusive or also disjoint if it's impossible for both events to occur simultaneously. So essentially the probability of event A and B happening is nothing. So getting a club and getting a red card is absolutely impossible. Those events are disjoint. Okay. So what ends up happening here is when you go to find the probability of event A or B occurring, this ends up just being 0. So you can directly add those probabilities together. So super nice when that happens. So again, we're going to be working a lot with surveys and analyzing those. So we're going to try to figure out in this next example, are these 2 events disjoint or not? So we want to see, can both events occur simultaneously? If so, they're not disjoint. But if it's impossible for them to occur simultaneously, they are going to be disjoint. So our first set of events is we have event A, which is randomly selecting someone taking a stats course. Event B is randomly selecting someone taking an English course. So if I'm trying to figure out if these are disjoint, I want to see, is it possible for both of these events to happen at the same time? So if you think about it, it is 100% possible that someone is taking stats and English at the same time. And it might even be you, since you're taking this course. If you were taking English right now, you are fitting in both of these events. So both can be true simultaneously. So these events are not disjoint. The probability of that happening does not have to be 0. Now, it could be when you actually take a survey, but it doesn't have to be. That's the key thing. Have to. If I think of this next example instead, if I randomly select someone treated with a certain medicine, and I randomly select someone who received no medication, it's impossible for you to be treated with a medication and receive no medication at the same time. That can never occur. If you're getting no medication, you wouldn't be in that first group. Likewise, if you are getting a certain med, there's no way you're not receiving any. So it's impossible to receive meds and receive no meds at the same time. So these are disjoint. Okay, so that's great. So if I was looking at the probability of selecting someone who treated certain meds or someone who didn't receive meds, I could just add those together. So now that we've got a little bit of the or down, we're going to jump over to a different type of end problem. Because what happens if we have 2 things that we're doing? We're doing event A and then event B. There's a different way that we can look at that particular probability. So to be successful in an end problem, both events have to occur. So to calculate that probability of event A and B occurring, what we're going to do is we're going to take the probability of A and multiply it by the probability of event B. Okay. So you have to be careful with this because depending on the problem, when you're going and calculating event B, you've assumed event A has already occurred. So a really good way to think about this is if we're flipping a coin 2 times. So in that event, if I look at all of those possible outcomes, you have heads on the first one, heads on the second, tails on the second, tails on the first roll, and then heads and tails. So if I want the probability of getting a tails twice, there is one way that happens out of 4 possibilities. But thinking about this with this multiplication, if you want the probability of getting a tail and a tail, you take the probability of getting the first event, which is a tail, timesing it by the probability of getting a second event, which is a tail. So that first event is you have a 1/2 chance of getting a tail, a 1/2 chance of getting a tail. So you have a 1 in 4 chance of getting 2 tails. So it's the same way as just looking at that sample space. So again, if you can figure out the entire sample space, amazing. However, when you have a big sample space, it's more complicated. So going about this manner is much more efficient. So we're going to do 2 different examples. We're going to do the same thing, but I'm also going to just change one word in each of these. So 2 cards are selected with replacement from a deck of cards. We want to determine the probability that 2 hearts are selected. And if you kind of peep to the next example, the word that's going to change is with and without. So with replacement is basically I'm going to shuffle this deck of cards, pull one out at random. I'm going to observe what that card is, and it goes right back in the deck. Shuffle it again, and then I'm going to draw my second card. So it's basically a reset on the deck of cards. So if you were to sit here and you were to figure out this sample space, you have 52 possibilities for the first draw, and then you go through and you put that card back in, you have 52 possibilities for the second draw. So you'd have to sit there and you'd have to pair up the ace of hearts, say, with all 52 other cards. And then you move on, you have to pair up the ace of diamonds with all 52 other cards. This would be really difficult for you to list out the entire sample space, where when it was just these 2, heads or tails, there wasn't a ton going on. So this is where multiplying these probabilities is going to be much better. So I have to consider 2 different draws. So for my first draw, my probability of getting a heart is 13 out of 52, or a 1 in 4 chance of getting that particular suit. Okay, so I have a 25% chance of getting a heart on the first draw. So when I'm calculating the probability that 2 hearts are selected, I'm assuming, great, the first event happened. So I've drawn that card, I've gotten a heart, which I had a 25% chance of occurring. That card then goes directly back in the deck. Okay. So when I go to find the probability of that second draw, I have a completely fresh deck. So I'm looking at the probability of getting a second heart. So I'll call this heart number 2. And I still have all 52 cards in there, and I can draw the same one again. So I still have a 13 out of 52, or a 1/4 chance of getting a heart on the second draw as well. So our probability of getting a heart and then another heart is the following. My probability of getting a heart on that first draw and then a heart on the second draw is the probability of getting a heart on the first draw. So I'll call that heart number 1. And we'll go ahead and even add that back up here. Multiplied by the probability of getting a heart on the second draw. So heart number 2. So we have a 1/4 chance multiplied by a 1/4 chance, which means I have a 1 in 16 chance of getting a heart 2 times in a row. Okay. So again, this way is much easier than sitting there and figuring out the total possible outcomes for this. Because realistically, we're going to talk about this soon. You have 52 times 52 events. So there's 2,500 possibilities for if you were to draw 2 cards in a row of what those outcomes would be. And you don't want to sit there and have to count which of those result in 2 hearts. Instead, it's much easier to consider these draws separately. Okay. But now if I do change this word slightly, if we select 2 cards without replacement from a deck of cards, we want to determine the probability that 2 hearts are still selected. So without replacement is going to mean that once I pick that first card, I look at it, it doesn't go back in, it sits on the side. So I actually have a smaller deck left over. So if I go to consider the first draw, really absolutely nothing has changed. So my probability of getting a heart on that first draw, so we'll call it heart number 1, is still 13 out of 52 or a 1 in 4 chance. Okay. But now that I've selected that card, the card we select is then removed. And it was a heart that's removed. So when I go to calculate the second draw, it's a little more complicated. So instead now, I had 52 cards, but I've removed the 1. So in total, I have 51 cards. And more specifically, I've removed a heart because the first event occurred. So I no longer have 13 hearts in the deck. I have 1 less. I have 12. So here, 1 heart is removed because the first event occurred. So my probability of selecting 2 hearts now is a little bit different. So again, when we're doing this end event, is I'm going to look at my probability of getting a heart on the first draw, and I'm going to multiply it by the probability of getting a heart on the second draw. Probability of getting a heart on the first draw is still the same. It's 1 in 4. However, I now have a 12 in 51 chance for the second draw because 1 card has been removed. So if we go ahead and simplify this, you can indeed multiply stuff out. However, 12 and 4 do simplify. 12 divided by 4 leaves me with 3. So ultimately, this leaves me with a 3 and 51 chance. And then this does actually reduce. Top and bottom are divisible by 3. So you have a 1 in 17 chance of this event occurring. Okay. So this one was a lot more complicated when we didn't have replacement. With replacement is much easier because everything stays the same. It's basically like you started from scratch. So when that happens, we actually say these are independent events. So events A and B are independent events. If the occurrence of either event in no way affects the probability of the occurrence of the other. So again, in that first example, when it was with replacement, I got to ignore the fact that I drew a heart already, and I could calculate that probability on its own. So independent events, this is when there is replacement, because it resets it. But in this last example, you could see this probability was changed because I had one less heart to draw from and one less card. So this second probability was affected. So in the prior example, the first event affected the probability of the second event. Instead of calling them independent, these are dependent events. And so anytime something is without replacement, you're going to have this occurrence. Okay. The second event is altered as a result of that. Okay. So unfortunately, small little words make a big impact on what ends up happening for our specific problem and probabilities. So just try your best. But really make sure you read carefully and pick out those keywords. So from here, we're just going to do one more example working with and and or problems, but we're going to do it with a survey. So the table below summarizes results from a study of people who refused to answer survey questions. So we have different age brackets, and we have the number of people that responded to the survey and the number of people that refused the survey. So we're going to find two things. We're going to start by finding the probability that a subject selected responded or is between the ages of 22 and 39. So I need to first with or, again, that is more inclusive. They can be between the ages of 22 and 39, or they could have responded. So if I start with the people that responded, that is everyone in this first row, okay? So the number of people that responded is we have to add all of those together. It's 79 plus 261 plus 251 plus 142 plus 144 plus 208. Okay. You can do this as adding the probability of each individually, then subtracting that overlap. However, if I also want the number of people that responded or are between 22 to 39, I'm going to look at those columns of 22 to 29 and 30 to 39, and I'm just going to add those extra individuals. So in this case, we have the 20 that didn't respond from the 22 to 29 group, and then the 33 that didn't respond. So the main thing is you don't want to double count. So I'm going to even move this down a little bit and add this as a note. Don't double count the individuals. So I don't want to double count these 261 and 251 people because I've already put them in responded. So if we add all of these together, the 79, 261, 251, 142, 144, 208, 20, and 33, you're going to see that there are 1,138 people that responded or are between the ages of 22 to 39. Now, if I want the probability of this happening, I also need my total number of people that were surveyed. And in that case, that means I need to go ahead and I need to add all of these together. Because unfortunately at the start, they did not give me the number of people that are surveyed. So I have to figure that out. So I'm going to start by adding the first row together: 79, 261, 251, 142, 144, 208, 11, 20, 33, 26, 35, and 57. If we add all of those together, there were 1,267 people that were surveyed. The other thing you could actually do, you've already added these together and got that it was 1,138. From there, just add 11, 26, 35, and 57. And that will reach you to the same total. So I have my number of people that make this OR event successful, and I also have my total. So my probability that the person responded or is between 22 to 39 is 1,138 out of 1,267 people. Okay. So this, not something that's easy to reduce. You're likely going to see that it's going to ask you for a decimal answer, and typically we round to 3 decimals. So if you plug this into your calculator, you'll see it is about 0.898, which means 89.8% of people responded or are between these ages. Okay. Now, if I want to change this slightly, and I'm going to change it to an end criteria, we're going to find the probability that a subject selected responded and is 60 or over. Okay. So in that case, the end means it needs to fit both criterias. So these are the people that responded, but only these 208 people also fit that second category. So they need to fit both categories here. So it's only the 208 people. And I don't have to go ahead and I don't need to figure out my total. I already did that in part A. I know how many people were surveyed. So the probability that they responded and they're over 60 is 208 out of the 1,267. And so if you plug this into your calculator, it's about 0.164 or 16.4%. Right. So we're going to keep checking with probability. We've got some more complicated situations to consider next. We're going to look more thoroughly at complements as well. And then we're also going to talk about counting.